Hello, and welcome to Alex Derives Stuff. Today, I wanted to take you on a little journey that I went on in my attempt to come up with a better way to compute square roots. It's a fruitless attempt because this is a well-studied subject, but I find it fun. So I'm going to share with you the stuff that I came up with, and then I'll show you that what I ended up coming up with was equivalent to something that was figured out a long, long time ago. So computing square roots, a journey from the bisection method to the secant method. Now, I will tell you that I didn't know at the time that what I came up with was called the secant method. I only found that out later, and we'll see why it is called the secant method eventually, towards the end. Okay. So first of all, what is the bisection method? So this was my starting point here. This is a well-known method for computing square roots. The basic idea is this. It's easiest to see if I do an example. So suppose we want to compute, say, the square root of 37. Okay, so the first thing we need to do is get some initial estimates. And they don't have to be terribly good. We could say, all right, it's between 6 and 7, right? Because, well, 6 squared is 36. That's a little bit smaller than 37. 7 squared is 49. That's bigger than 37. So, yeah, the square root of 37 is somewhere between 6 and 7. So we can plop those on this little number line I have here. Cool. Now, so what the bisection method does is we just find the midpoint of the interval, so 6.5. And so then we check to see what side of 6.5 square root of 37 is. So if we square 6.5, we end up with a number that's bigger than 37. Okay, so that means 6.5 is too big. So that means that the square root of 37 is somewhere in between 6 and 6.5 here, right? Like this 6.5 is to the right of the square root of 37. Okay, so then, zoom in. Now we've got, all right, so square root of 37 is somewhere in between these two numbers, and we repeat the process, right? We find the midpoint, 6.25 in this case. We square it. Once again, we got a number that's bigger than 37. So that means, okay, so 6.25 is to the right of the square root of 37. Okay, so root 37 is between 6 and 6.25. So zoom in again, and then we cut this in half, and we find the midpoint again, and we square that number, and yet again, we get a number bigger than 37. So 6.125 is bigger than square root of 37, so that lies somewhere in here. Now, lest you think the square root of 37 is always going to be on the left half, let's take a look at this. We got 6.0625 is our next midpoint for this interval. And then we square that number and we get something smaller than 37. So now we know that, okay, 6.0625 is smaller than the square root of 37. So that means that our square root of 37 is somewhere in the right half of this interval. So, okay, so and we keep going and going and going, and you can see each time we cut our knowledge of the square root of 37 in half, right? Or I guess we double it, right? We narrow down our interval where the square root of 37 lies by half. Okay, so this is what we've computed so far. I plugged these numbers into Google Sheets, right? And so I've got my lower, so I've got the step number over here, got my lower bound, my upper bound, and then my sort of next one, and then my check to see whether this is a lower bound or an upper bound, right? And if we kept going until step 28, so we'd get, okay, these two crazy numbers for the square root of 37. All right, so we know that this number right here is definitely less than square root of 37, and this number right here is definitely bigger than square root of 37. So we know after 28 steps of this, trust me, I did the work, I coded it up. We end up with square root of 37 is somewhere in between those two numbers. And don't focus so much on the actual digits of these numbers. They don't matter as much. Well, I suppose they matter, but what matters is the digits that these two numbers have in common, the 6.0827625, Both of those have those first, I guess, what is that? 1, 2, 3, 4, 5, 6, 7 decimal place, 7 digits after the decimal point are the same. So we know that those yellow digits are correct. And then we know that the 8th digit is, well, it's either 2 or 3. It's off by less than 1. So that's pretty good. So we can confidently say that the square root of 37, if we just cut this off at the 5 here, that the square root of 37 is approximately equal to this number. So after 28 steps, seems like a lot. There are other methods that are way slower though. We calculated square root of 37 to an accuracy of 7 decimal places. Okay, cool. So, all right, like I mentioned, the 28 steps seemed like a lot. So this method has what you might call fixed accuracy. Every time we use this method, or every time we go through one iteration of this thing, we cut the error in half, right? The size of that interval where we know that the square root of 37 lies gets cut in half. So that means if you iterate it n times, the error is around 2 to the minus n. The error is like just the size of that interval. We know square root of 37 is between here and here. So if you wanted to get the accuracy of a calculator with, say, float 10, so that's like 10 digits after the decimal point, this would require 34, sometimes 35 iterations. Okay, so every time you compute a square root, you'd have to run through this process 34 or 35 times. All right, so here's a question. Is there a way to alter this procedure to get answers more quickly? And this was the question that this was my starting point right here. This is what I wanted to do to come up with my own method. And so my attempt here was an accidental reconstruction of the secant method, and it's not obvious at all from the way that I'm going to go about this at first that this is something called the secant method. But so the idea is if we compare to the bisection method, is we took two estimates, a lower estimate and a high estimate, so one that's too low, one that's too high, and we used it to generate a new estimate. So we basically say if we know that square root of n is between L and H, then we can get a better approximation by saying square root of n is approximately the average, the midpoint of L and H. So, well, we don't have to choose the midpoint. We could choose any point between L and H as our next estimate. And perhaps we could make a more educated guess here. So if we look at the example from before, calculating square root of 37. All right, I'll draw this little number line. There's 6, there's 7. Okay. Now, if you look at the numbers, right? So like, okay, we're finding square root of 37. So 6 squared is 36. That's pretty close to 37. 7 squared is 49. That's pretty far from 37. So you'd sort of assume that the square root of 37 is a lot closer to 6 than it is to 7, just based on that alone. And that's the genesis of this method right here. Okay, so if we draw this other number line, okay, we'll put the squares of the numbers here. So 36 and 49. If you sort of track where 37 lies in here, it lies about there. It's probably actually a little bit closer. So if 37 is there on this bottom number line, then a more reasonable guess would just be that same relative location on the top number line. And we just have to figure out where that is. So that point is the same proportion of the way. So we'll call this point X, right? And we want X to be the same proportion of the way between 6 and 7 as it is between 36 and 49. Okay, that's the idea behind this method here. Okay, so how do we calculate this? Well, all right, well, we find this little distance right here. So we basically say this little distance, that's this 37 minus 36. And we can divide it by the total distance for the bottom number line. So that would be 49 minus 36. Cool. And we could just say that's equal to the same ratio for the top number line. So that for the top number line, that little distance, that little blue distance there would just be whatever x is, minus 6. Okay, cool. And then divided by the length of that number line. So that's 7 minus 6. Oh, cool. And then we could chug along here and solve for x. So if we do that a little bit, clean it up a little bit, We get 1 over 13 equals x minus 6 over 1. I suppose we can get rid of the over 1. We could add the 6 over. And so we could actually, it wouldn't be bad to say 6 and a 13th, to be honest. But I like to write this as a improper fraction. So if we do that, that's 79 over 13. And so this is our next guess for the square root of 37 using this method. And so it's related to the bisection method because we're picking a point in between our lower bound and upper bound, but we're making a more refined guess than what we did originally. Okay, so we've now got, all right, a good approximation for square root of 37 is 79 over 13. So important question whenever you're approximating things is how good is this approximation? Well, if we write that 79 over 13 as a decimal, we get this. Okay, that doesn't really tell us anything. If we square it, I used a calculator, I'll be honest. We get this like 36.92899. So we get this number that's a little bit smaller than 37. So, okay, well, I mean, the square root of 37 certainly is, it's definitely, or the square root of 37 is definitely bigger than 79 over 13. Or 79 over 13 is too small, but it's not too small by much. So interesting. So at this point, what we can say for sure is that the square root of 37 is between 79 over 13 and 7. But I don't know, 7's really far away from it, right? Like, so maybe we can tighten up the number on top. And at this point, this is when I just started experimenting. I just sort of thought to myself, well, all right, 79 over 13, that is really close to the square root of 37, because if I square it, I get a number that's really close to 37. So what if I just, I don't know, upped the numerator by 1? What if we tried 80 over 13? Is that bigger than square root of 37? Well, let's see. Holy moly, if we do 80 over 13, we do, in fact, get a number that's bigger than 37. So that means 80 over 13 is bigger than square root of 37. Holy cow. Okay, so we've tightened this significantly right here. We got like one step. So after one step in the bisection method, we had an error of a half. And after one step in this method, we have an error of 1 over 13, right? If you do the h minus l, you get 1 over 13. Cool. So then we can run through it again. So let's see what happens if we run through this again. So we now have, all right, I'm not going to write out what those square numbers are. 79 over 13. If you work out where 37 lies on this bottom number line, it's about there. This is, a rough sketch. And then, okay, so we figure out where's that. And bleh. All right, we have that same proportion, right? It's the little distance over the big distance on the bottom number line. That's the same thing as the little distance over the big distance on the top number line. Okay, and we solve this for x. I won't bore you with the details of me solving for x. And we get this number right here. Okay, and if we take that number and square it, we do get a number that's smaller than 37, but not much smaller, 36.999587. Okay, so but it is an underestimate. So we know that this number is less than root 37. Okay, let me pause here to say that, all right, in the course of coming up with this, I tried out this method for a whole bunch of different square roots. And every single time I ran through this thing, and I did this little computation here with the number lines to work out what my next guess was going to be, I always ended up with a number that was smaller than the square root of 37. And so I went ahead and I just conjectured, like, all right, so maybe I'll always get an underestimate this way. And another thing that happened is I always ended up, if I increased whatever I got for this next guess, if I increased the numerator by only 1, because I kept expressing them as fractions, if I increased the numerator by 1, I always ended up with an overestimate. So let's check. So here, if we take that, bump it up by 1, so that, and we want to see, like, well, is that bigger? So if we square that, again, I won't bore you with the details of the computations, we get that number. And that's bigger than 37. Again, not much bigger. And so now we know that square root of 37 is between 12,573 over 2,067 and 12,574 in 2,067 for an error of 1 over 2,000. Holy cow. So what's going on here? So now if we write those two numbers as decimals, we can see we get the first two decimal places correct, and then the third decimal place is off by 1. And in fact, you could sort of say it's off by a half because it's like 2.7 versus 3.2, right? So yeah, so like these two numbers are less than 1 in 1,000 apart. Okay. So if we're comparing this to the original bisection method from before, then uh, 2 iterations gives us an accuracy of better than 1 in 1,000. And actually, you saw before, it's like 1 in 2,067 versus 2 iterations of the bisection method gave us an accuracy of 1 in 4 because we like, okay, so first iteration gave us an accuracy of a half, second iteration gives us an accuracy of a quarter. All right, so this is a vast improvement right here, but there's a couple of things that I'm being very wishy-washy about. One, so we have to state these as conjectures. So conjecture number 1 is that, okay, so when I compute the next guess this way, I'll always get an underestimate. I'll always get a number smaller than root n. And then my second conjecture has to do with that upping the numerator by one thing. So if we write our next guess as a fraction, then when you increase the numerator by 1, you'll get an overestimate for square root of n. So, all right, and so these are things that have to be proven about my method. I was being very, I based this off of like numerical evidence. So in order to figure out stuff about these conjectures, we need to come up with formulas, basically. We need to figure out, like, okay, what's a general formula for calculating the next guess? So, all right, so if we just have initial estimates, L and H. So we know from the get-go that L is less than square root of n is less than H. So square root of n is between those two numbers. I suppose we can assume L is positive. And we do the same number line here. We put L squared there and H squared there. And let's say N would be there. This would be on the bottom number line. And we want to locate our next guess there. Okay, so same thing. So if we set up our same proportion, our next guess is just X. We're just doing the little distance, X minus L, over the big distance, H minus L on the top number line. That should be equal to the little distance over the big distance of the bottom number line. So n minus L squared divided by H squared minus L squared. Okay. And by the way, to give you a sneak peek of what's coming up, this might have something to do with lines because this looks like setting two slopes equal to each other. All right. So now we take this thing and solve for x. Okay, so I just factored the denominator, the h squared minus l squared becomes that. And hey, we can cancel out those h minus l's. And there we go. And then just add the L over to the other side. And so we get X. So our next guess is this L plus n minus L squared over H plus L. And if you want, you can like get a common denominator and write it as a single fraction. Cool. So then, okay. So if my first conjecture is true, then this quantity right here is definitely smaller than square root of n. So let's see. We can do this algebraically. So we wish to show that square root of n is bigger than that thing right there, using only the fact that L is smaller than square root of n, and also square root of n is smaller than h. Okay, so we can equivalently show that the square root of n minus x is positive. I tend to find it easier to write these like this. It's easier for me to tell whether something's positive or negative than if one thing's bigger than another thing. Okay, so if we want to do this, we just want to plug in for the x. Okay, and I put a little question mark over the inequality here, right, because I don't know that this is positive yet. That's what I'm trying to prove. So basically, what I'm going to do is I'm going to just manipulate this left-hand side, which is just root n minus x. and just show that what we end up with when we simplify that has to be positive. So one thing we can do is we can distribute this minus sign through the parentheses. And so if we do that, it's like n minus L minus this crazy fraction. And the next thing we can do, it's not necessarily obvious, is we can think of this n minus L squared as a difference of squares, and we can factor that. So square root of n minus L times square root of n plus L. And the reason for that is, check this out. Over here, we've got a square root of n minus L, I guess times 1, right? And then over here, we've got a square root of n minus L times this other stuff. Oh, cool. So we can factor out the square root of n minus L. And here's what, so basically I put little parentheses around that first one. So if we factor out the square root of n minus L, we'll get 1 minus this root n plus L over h plus L. Okay, so cool. Now if we do a little common denominatoring, okay, so the 1 becomes h plus L over h plus L, and then we can see because this is h plus L minus root n minus L, so the L's will cancel, and the numerator will end up being this thing, all right, h minus root n. So okay, so root n minus L, hey, that's positive because root n is bigger than L. And then there's h minus root n, that's positive because h is bigger than root n. So both of these things are positive, which means this is true. Okay, cool. So, all right, so we've proven our first conjecture anyway, that, all right, so according to our algorithm here, then if L is less than, if square root of n is between L and h, and we compute a next guess, x equals this thing, then we always know that x will be less than square root of n. By the way, the x will always be bigger than L, so it'll always be a better guess than L was. Now for the second conjecture, how do we come up with this, right? Like we need to rewrite our things as fractions. So what we could do is, instead of L, we could rewrite the L as like some number divided by some other number. So we could rewrite the L as P over Q and the H as P plus 1 over Q. And we can assume that we start off with an estimate that's like this. And then if our estimate is like this, we want to take our original guess and just rewrite it in terms of these numbers, right? These P's and Q's here. So just replace the L with P over Q and the H with P plus 1 over Q. And if we do that, we end up with this gnarly looking thing, and we can simplify it. Okay, that was multiplying top and bottom by Q squared, and then we can clean up that denominator, and we can get a common denominator, and then we can combine the numerators, and what we end up with is this. Okay. I'm confident that you can get to this point. That's why I rushed through that. Okay, so then now if we consider the x to be a fraction, we consider our new numerator to be, say, our new p, a p prime, right? Shiny new p. And then our new denominator be q prime. So this p prime would be this p times p plus 1 plus n times q squared, and this q prime would be this. This is the same next guess as what we had before. It's just if our L happened to be P over Q and if our H happened to be P plus 1 over Q. So our second conjecture boils down to this. So if we start off with a P and a Q so that this is true, then we calculate the numerator of our next guess and the denominator of our next guess. And then the conjecture itself is that if you do all of this, then the square root of n is smaller than p prime plus 1 over q prime. We already know that p prime over q prime, is less than root n. And we know if we just add 1 to the new numerator, then that's going to be an overestimate. All right, I'm not going to prove this here. I will tell you that I have proved it, and it took a lot of work. Like about a quarter of a notebook of graph paper with lots of ripped out pieces of paper thrown in the garbage and crumpled up. I crumpled them up and then threw them in the garbage, not the other way around. And and I had to use a whole bunch of tricks, nothing like super advanced, but just random, just like weird stuff with calculus. And I was finally able to prove this. And then once I found out that this is the secant method, then it turns out there's a way easier way to prove it than what I did, and that's what we'll get at next. So why the heck is this called the secant method? All right, well, all right, so first of all, I've been working with like two number lines and doing little proportions with the two number lines. What we can do instead of drawing two separate number lines and lining them up is instead of making them parallel to each other, we can make them perpendicular to each other. So I could flip it this way, and we could slap a little graph on here, and we could just put a graph of like y equals square root of x, right? Because we're approximating values of this function. So there's a rough cartoon of y equals square root of x. And I want to emphasize that this is a rough graph, so there's not a lot of accuracy with this. The only points that are accurate here are these 2 points, the ones that I know, L squared L and H squared H. And then we could draw a line between these 2 points. So for computational purposes, we're able to figure out points on the line, and we're trying to use points on the line, use like y values on the line to sort of estimate y values on the curve. All right. I will say this is definitely not to scale, whatever my L and H are. So in this curve, it looks like probably a little too flat at the ends. It's probably not quite the same thing as a square, but it will serve for visual purposes. Okay, so what we were doing before was equivalent to making our next guess be we just draw, well, we know where n is, right? Because that's the number we're trying to find the square root of, and we just find the point on the line where the x coordinates equal to n, we just figure out what's the y coordinate on the line there, and then that would be our next guess. All right, well, what do we do with this? Oh, all right, let's just call this L prime. All right, so let's say our next guess is L prime. I think I was calling it x before. All right, so we can calculate this slope two different ways, right? We could basically just say, well, I could do the big slope, right? So the slope between here, L squared L, and here, H squared H. And if we do that, okay, that's the slope of the line between there. If you want to factor the bottom and clean this up a little bit, feel free. And then we can also find the slope between this point here, L squared L, and this point, which is N comma L prime, and the L prime is our next guess. So that would just be the change in Y, L prime minus L, divided by the change in X, N minus L squared. Cool. And so basically, because both of these are the slope of the same line, we just set them equal to each other, right? Because they're supposed to be the same. And so now this right here, I guess it's not quite the same. If you rearrange it a little bit, I think if you swap the h minus l and the n over n minus l squared, then you end up with the same proportion that we were using before with just the number lines right here. So we are calculating the same thing. And so if you solve for the L prime, we get this same thing that we got before, the L prime equals L plus that. Okay, cool. All right, so what we were doing with that little proportion thing is equivalent to this. This linear interpolation is what this is called. Okay, now, but because we've got this graphical interpretation here, we can calculate an upper bound, and I'll give you a sketch of how to do this, and I'll leave the details as a nice little homework problem for you. So basically, what we could do is then this is the computationally heavy part. We need to figure out the maximum vertical distance between the line, the secant line, the yellow line, and the curve. So, and for that, so the idea is that, if I'm right here, the vertical distance is small. If I'm right here, the vertical distance is a little bigger. Right here, then maybe that's where it is. And the point is that you can calculate that. And so we could say like that's the biggest suppose this point is the biggest vertical distance between the line and the curve. And let's call it D max right here. So since there aren't any vertical lines vertical distance is bigger than this between the line and the curve, if I go over here to where I want my estimate to be, then I know that, well, if I go that same distance above this point, then I'll overshoot the curve. And maybe it's only a little bit, but yeah. Okay. So then the y coordinate at that point would be an upper bound. So that'll be our h prime, right? And so our h prime is this, whatever this distance d max is above L prime. So, all right, cool. All right, so that's what the secant method is. And um, so to leave you with a little bit of homework, don't worry, it's not too hard. And I've got you sort of walk through it here to clean up some loose ends. What we can do is, so first, find the equation of this line, right? So, okay. If you look back in the presentation a little bit, you might be able to actually, it is in a sneaky way actually written in previous slides, but it's easy enough to find. If you have 2 points, you can figure out the equation of the line. So then, so I'm going to have this function d of x. If that's the vertical distance between square root of x and the secant line, whatever the equation is, then find the max value of d of x. So in other words, what's this d max, right? And so that's the part where you got to do a little bit of calculus, right? So our d of x will be square root of x minus whatever the equation of the line is, right? Minus quantity mx plus b. Okay, and then that'll be the d max, and then that'll allow you to calculate what the h prime is, all right, what the upper bound is. And what's nice is if you just write it in terms of L and H, it's actually a nice and simple form. And then the last thing is we can use this to prove conjecture 2 from earlier. And I've got a little cleaned up version right here, where once you figure out this d max, if L, so if you set L equal to P over Q and H equal to P plus 1 over Q, then this d max, because if you think about it, the d max is basically the error in our upper and lower bound, that's less than 1 over, this is what Q prime was, the Q times 2P plus 1. And this is a little sneak peek of the answer here. What you end up with is about a quarter of this, actually. So, all right. So feel free to finish the job for me right here. And I will post some follow-up videos where I'll use the results from these things. And in fact, coming up on Alex Derives stuff, I want to do a deeper dive into how accurate this method is. And it compares favorably. It's not quite as good as Newton's method, which is the sort of standard way of doing this. And I'm also going to show you how to code this up in Google Sheets. You might think Google Sheets, like Excel coding, what? But yeah, you can write code in those things. And I also want to show you how to generalize this a little bit. These will probably all be separate videos. And so, like, well, can I only do square roots with this method? Can I do other things? Can I do cube roots? Can I do things like sines and cosines, stuff like that? And then also, this is the fun part, and this is the part that is sometimes left out of these things, which is what could possibly go wrong. All right, so this is something whenever you're trying a new technique for computing something or for doing any kind of thing, it's always a good question to ask. What could possibly go wrong? I know in like horror movies and stuff, if you ask this question, then you immediately die. But in this case, it's in general in the real world. This is a good thing to ask because yeah, you need to know the failure modes of the things that you're doing if you want to use them successfully. So that's all I've got. I hope you try out the homework. And I will see you next time with one of these topics.